All right, let's take another look at another group of acids. These are called oxyacids. And so in oxyacids, we have an H connected to some kind of oxygen containing generally polyatomic ion. So generally we have a hydrogen that's bound to an oxygen, and then this oxygen is bound to some other element, which can then be bound to further elements, right? So we have hydrogen, oxygen, and then some other atom. And so if we think about the bond that's going to break, it's going to be this bond right here, this OH bond, right? So the strength of the acid depends on how strong this bond is. Where the weaker the bond, the stronger the acid. Right? The weaker the bond, the stronger the acid. The stronger the bond, the weaker the acid. And so if we kind of think about what's going to make this bond weak or strong, it's the same case as before of how much electron density we have on this bond. And so what we have here is, some electrons on this Y, some electrons on this oxygen, and then some electrons in this bond as well. The more electronegative your Y is over here, the more it's going to pool on these bonds, and then the less electrons are going to be left to have between this OH bond, and then the stronger the acid that you're going to have, right? So we'll say the more electronegative atoms pool harder on these electrons. So example, HOCl versus HOI, right? Before it was kind of flipped because of the size, but now we're just talking about electronegativity, right? Chlorine is more electronegative. So it's pulling on these electrons further or stronger, which makes this a weaker bond, which makes HOCl overall the stronger acid. And so you can see that in this chart, as the electronegativity increases, the Ka increases. We get more and more acidic, right? The overall size of these elements is not important anymore because they're no longer directly bonded to the hydrogen. And we're not talking about breaking a bond between, in this case, the halogen and the oxygen. We're talking about breaking the bond between the oxygen and the hydrogen. So when you have the more electronegative element, you will have a stronger acid. But what if they're the same element? So for example, HNO2 versus HNO3, nitrous acid versus nitric acid. Well, let's draw their Lewis structures. Right, and so we can tell immediately a big difference, right? This nitrogen actually has a positive formal charge, while the other nitrogen does not. And technically, we don't even have to draw the Lewis structures. We can think about their oxidation states, So remember, oxygen is always -2, hydrogen is +1 with nonmetals. So this ends up with a +3 oxidation state. While this one over here has a +5 oxidation state. And so if you think about it, the higher the oxidation state, the more positive it is, the more it's going to pull on those negatively charged electrons, which is going to make that OH bond weaker, and you're going to have a stronger acid. So we say higher oxidation state, say pulls harder. And so we have the stronger acid. So in general, the more when we're talking about oxyacids, the more oxygens you have, the higher oxidation state you're going to have, and the more acidic your compound is going to be overall. So there's some pictures to show that. Here's kind of the chlorate series from perchlorate to hypochlorite, and in their acid form, right? So we can see when we add more oxygens, we get a stronger and stronger acid. Whereas when we have less oxygens, we get a weaker acid, right? Because of the oxidation state of the central atom, causing this OH bond to either be weaker or stronger. And same thing for other oxyacids as well. Of course, you want to compare only the same element. So you can compare, for example, nitrous acid and nitric acid to each other, right? Or you can compare sulfurous acid to sulfuric acid, right? The higher the oxidation state, the more acidic it is overall.